subset of edges such that each vertex belongs to exactly one of the edges in that subset. So here in blue, you see I selected 3 edges. These edges in blue are called the dimers, and each vertex is exactly on one blue edge. This is not the only dimer covering of this graph. This graph actually has 3 dimer coverings, which are these 3 configurations. And the dimer model consists in putting a probability measure on the set of dimer coverings of a given graph. So one natural probability measure is the uniform probability measure, but actually we are going to consider more general probability measures called Boltzmann measures. And for this, we will extend the setting. We have a graph with edge weights. Each edge carries a positive real number. And we define the weight of a dimer covering to be the product of the weights of the dimers. For example, here, the weight of this dimer covering is C times D times E. And we use these weights to define a Boltzmann probability measure on the set of dimer coverings. We draw a dimer covering at random with probability proportional to its weight. For example, we will get this one with probability CDE divided by the sum of these 3 quantities. And if you take all the edge weights to be equal to 1, you recover the uniform probability measure. What do we want to do with such a model? So such a model was introduced by physicists in the 1930s to study the adsorption of diatomic molecules at the interface with a crystal. And what we want to compute is first the partition function, that is to say the sum of the weights of all the configurations, and also the correlations. For example, you have 2 edges in your graph and you want to compute the probability that both edges appear as dimers in a random dimer covering. These questions are in general very hard to answer, but physicists in the 1960s noticed that if your graph is planar, then these questions have a simple solution. So I'm going to restrict myself from now on to planar graphs, and moreover, to make things a bit simpler, I will require my graphs to be bipartite, meaning that I can color the vertices in black and white in such a way that white vertices only have black neighbors and black vertices only have white neighbors. Another way to say that the graph is bipartite is to say that every cycle must have an even length. So my setting is planar bipartite graphs with positive edge weights. A remark is that if you look, for example, at this white vertex and you multiply the edge weights of all the edges incident to that vertex by 2, then you do not change the Boltzmann probability measure. Why? Because each dimer covering contains exactly one of these 3 edges. So this means that the weight of each dimer covering will be multiplied by 2, so you are not changing the probability measure. More generally, if you pick any vertex and you multiply by lambda the weights of all the edges incident to that vertex, this is called a gauge transformation, you do not change the probability measure. And if on your graph you have 2 different collections of edge weights which are related by a sequence of gauge transformations, potentially at different vertices, these 2 collections of edge weights are called gauge equivalent. So since what we care about are not really the edge weights, but rather the Boltzmann probability measures, what we are going to consider are not just the edge weights, but collections of edge weights quotiented out by gauge transformations. And on that space, edge weights modulo gauge transformations, we have some nice variables called the capital X variables, which live on the faces of the graph. So how do I compute a capital X variable? For example, look at this square face. I'm going to take the alternating product of the edge weights around this face, meaning that I am turning in the counterclockwise direction around the face, and when I go from a black vertex to a white vertex, I put the corresponding weight in the numerator, and when I go from a white vertex to a black vertex, I put the corresponding weight in the denominator. So for this face here, the alternating product is A divided by C times F divided by V. And same for the other face. So these X variables provide coordinates on the space of edge weights modulo gauge transformations. And you notice that if you multiply by 2, you do a gauge transformation somewhere, you see that this x variable, in the numerator, the f is multiplied by 2, in the denominator, the d is multiplied by 2, so it doesn't change the x variable. So now, how did the physicist compute the partition function and the correlations for planar bipartite dimer models? Is by using some tool called the Castellane Matrix. So you start with a planar bipartite graph with positive edge weights, and we're going to compute a Castellane matrix. This Castellane matrix is not a deterministic function of these edge weights and the graph. We need to add in some more information. And this additional information is a sign on each edge of the graph, which needs to, this assignment of signs should satisfy a certain condition called the Castellane sign condition. What is this condition? Whenever you have a face, so each face, I recall, since the graph is bipartite, has even degree. So it's either degree 0 modulo 4 or 2 modulo 4. The Castellane sign condition says that whenever you have a face of degree 2 modulo 4, then there should be an even number of minus sign around that face. And whenever you have a face of degree 0 modulo 4, then you should have an odd number of minus sign around that face. So let's look, for example, at this square face. You have 1 minus sign around it, which is odd, so it's fine. Same for this one. And then you may claim that there's also the outer face here of degree 6, and there are 0 minus sign, so it's fine too. Actually, you just need to check that the Castellane sign condition is satisfied on each bounded face, and then it will automatically be satisfied on the outer face. So Castellane showed that actually any graph carries a Castellane signing, but these Castellane signs are not unique in general. And using these Castellane signs, you can define the Castellane matrix. The rows of the Castellane matrix are indexed by the white vertices, and the columns are indexed by the black vertices. So for example, in position 1, 1 of the Castellane matrix, you need to look at white vertex number 1 and black vertex number 1. They are connected by one edge with positive edge weight C and Castellane sign plus, so you multiply out the plus and the C, and you get C at this position. At position 2, 2, between white vertex 2 and black vertex 2, you have D and minus. You multiply them out and you get minus D. At position 1, 3, between white vertex 1 and black vertex 3, you don't have directly an edge, so you have a 0. So the Castellane matrix K is the weighted signed adjacency matrix of this bipartite graph. So here I defined Castellane signs to take values either plus or minus, but we can do something slightly more general, and allow the Castellane signs to be any unit complex number. So now the Castellane condition is the following. So you assign one unit complex number to each edge, and the condition is that whenever you take the alternating product around the face of degree 2 modulo 4, then this alternating product should be 1. And if you take the alternating product around the face of degree 0 modulo 4, this alternating product should be minus 1. If you only restrict yourself to signs plus 1 and minus 1, you recover the previous condition. And you can again define the Castellane matrix by multiplying out the complex sign with the positive edge weight. So Castellane matrices are not unique. They depend on the choice of the Castellane signing, but whatever choice of Castellane signing you take, you will still get the following result. If you take the absolute value of the determinant of such a matrix, this will give you the partition function of a dimer model, the sum of the weights of all the dimer coverings. And if you want the dimer correlations, these are given by minors of the inverse Castellane matrix. These were results found by Castellane, Temperley, and Fisher back in the 60s. So the classical approach to these Castellane signs is to say that whether you have real Castellane signs or complex Castellane signs, that you have two numbers on each edge. You have one which is physically relevant, which is the positive edge weight. It's physically relevant because if you increase one positive edge weight while keeping all the others fixed, this will increase the probability that this edge is selected as a dimer. And then you have on this edge another quantity, which is the Castellane sign, and which was considered for a long time to be just like a computational trick, an algebraic trick. And there's a more modern approach to these Castellane signs, which consists in merging these two elements over each edge. You multiply out the positive edge weight with the Castellane sign, and you get a complex edge weight. And we will see in the rest of the talk that actually these complex edge weights carry a geometric meaning.
Sanjay?
Yes?
Couldn't you go even one step further and take, instead of a complex, some element of some group, like some UN or some...
Maybe, but then, I mean, to take the determinant of the matrix, you need to be careful because things don't commute, so you need to take...
That's true.
So
in principle, because I remember having seen some paper with supersymmetric kind of
yes,
expressions for
there are things like that, and I think Kenyon has some work on that. Yes.
Like you replace I by a 2x2 matrix.
Right. Right. So then it will be counting different things. It's maybe useful when you have some model on surfaces and you want to look at the monodromy of certain.
My question was, why stop at complex, basically, in this generalization?
In this talk, we won't need more than complex, but you can go beyond complex. And please feel free to interrupt if you have any questions in general. All right, and so when you have these complex edge weights, the Castellane sign condition is translated as follows. You should take these complex edge weights around the face and take the alternating product. This alternating product should be real positive if the face has degree 2 modulo 4, and should be real negative if the face has degree 0 modulo 4. Because you can just separate this alternating product of complex edge weight as the alternating product of the positive edge weights, which is always positive, and the alternating product of the complex signs. So now let me go to a different story and tell you about circle patterns and centers of circle patterns. So a circle pattern for a graph G is a way to draw a certain planar graph G. So for me, a planar graph is a graph that can be embedded on the plane, but which does not carry any specific embedding yet. So it's just some combinatorial data, a collection of vertices, a collection of adjacency relations, which vertex is adjacent to which vertex, and around each vertex, a cyclic ordering, the cyclic ordering in which you see the neighbors of that vertex. And a circle pattern for a planar graph G is a way to draw each vertex of the graph on the plane in such a way that every face is cyclic. So there is a circle, a circumcircle going through all the vertices around any given face. So for now, I'm restricting myself to bounded faces, only the bounded faces, and I forget about the outer face for now. So there will be some issue with boundary conditions. I will deal with these issues later, but for now, just bear with me and forget about boundary issues. So this type of object was introduced in discrete differential geometry because circle patterns served as discretizations of conformal maps. So for now, I just require that I have a drawing of my graph, not an embedding, meaning that in that drawing, two edges may cross outside a vertex, or you can have faces that are folded over. Once you have a circle pattern for G, you also have some natural drawing for the centers, for the dual graph of G. So what is the dual graph of G? You place a dual vertex inside each face of G, and you connect two dual vertices whenever the corresponding two faces share an edge. And there is a natural point where you can place this dual vertex because this dual vertex corresponds to a face and this face corresponds to a circle, so it's natural to place that dual vertex at the center of the circle. So given a circle pattern for G, you get a drawing of the dual graph of G. But you have here less information than in the whole circle pattern for G because you only have the position of the centers. Whereas in the circle pattern for G, you had the position of the centers and the radii. And here again, I insist, I just require that I have a drawing of the dual graph of G, not necessarily an embedding of the dual graph. And so the question is, I have less information with the centers than with the entire circle pattern, how much information am I losing? For example, can I recover the entire circle pattern from just the data of the circle centers? If the answer is no, maybe I have several circle patterns which have the same centers, then how many circle patterns do I have which give the same centers? And another question, if I just start with an arbitrary drawing of the geograph of G, not necessarily coming from circle centers, do I have a criterion to test whether this drawing corresponds to centers of some circle pattern for G? And I'm going to give you the answers to all these questions in the case when G is a bipartite graph. So here I'm going to show you a small animation on GeoGebra, and it will involve this planar bipartite graph, which is a portion, a 3x4 portion of the square grid. So here is a circle pattern for that graph, and you notice that if you look at these two vertices here, they are the two intersection points of these two circles, which means that if I draw the line connecting the two centers of these two circles, these two vertices are symmetric with respect to that line. What does this mean? This means that if I know all the centers of the circle pattern and I know the position of a single vertex in the circle pattern, for example, that white vertex, then I can recover the position of all the other vertices by just drawing the lines connecting centers and reflecting. For example, I reflect this vertex across this line, I get this black vertex, and I reflect across that line, I would get that white vertex, and so on. Now, what happens if I only know the position of all the centers? Where can I pick the position of that white vertex to get a circle pattern? Actually, the answer is that I can pick the white vertex to be anywhere, and for any choice of the position of that white vertex, I will get a circle pattern. So the answer to the first question is that there is a two-parameter family of circle patterns with the same circle centers as the original circle pattern. It corresponds to the fact that I can choose freely the two coordinates of one vertex. Now let's move to the second question, and for this let's consider this dual vertex, this circle center. I'm going to draw the lines connecting this dual vertex to its four neighbors in the dual graph. And you notice that if I start with this black vertex and I reflect across that line, I get this white vertex. Then I reflect this white vertex across that line, I get this black vertex, which I reflect across that line, I get this white vertex, and I reflect back across that line, and I come back to my starting point, this black vertex. What does this mean? This means that the composition of these four reflections is the identity. Why? When you have a composition of four reflections, and here it's very important that my graph is bipartite, because my graph is bipartite, all my faces have even degree, and so I have my dual vertex has an even degree. So I'm doing a composition of an even number of reflections. The composition of an even number of reflections is a rotation. And since all these lines are going through a common point, it's a rotation whose center is precisely the center of that circle. And I just told you that I have a fixed point for that rotation, which is that black vertex, which is distinct from the center. This means that this rotation is the identity. So now let me rephrase this fact, that the composition of the four reflections is the identity. You know that when you have two reflections, the composition of two reflections is a rotation centered at the intersection point of the two lines and with angle equal to twice the angle between both lines. This means that the composition of these four reflections is a rotation of angle twice the sum of these two angles. So to summarize, this means that when you start with the circle pattern, around each dual vertex, if you take the sum of every other angle, sorry, I missed something. So the sum of these two angles, twice the sum of these two angles should be equal to 0 modulo 2 pi, because this rotation is the identity. This means that the sum of these two angles should be 0 modulo pi. this is what it means that this rotation is the identity. So in general, whenever you have centers of circle patterns, if you take the rays connecting them to their neighbors and you take the sum of every other angle, this sum should be equal to 0 modulo pi. And the converse is actually true. If you start with an arbitrary drawing of the dual graph which satisfies this condition that the sum of every other angle is 0 modulo pi, then this indeed corresponds to some centers of some circle pattern. Let me go back to the PDF and summarize this for you. So from now on, I will always assume that my graph G is bipartite. If I start with a circle pattern, I have a 2 real parameter family of circle patterns with the same centers. And if I start with an arbitrary drawing of the dual graph for G, then this corresponds to centers for a circle pattern if and only if around each dual vertex the sum of every other angle is equal to 0 modulo pi. So this is if I start with an arbitrary drawing of my dual graph. Now if I start with an embedding of my dual graph, the condition for that embedding to correspond to circle centers for G is that around each dual vertex the sum of every other angle should be equal to pi modulo 2 pi. So it's not either 0 or pi modulo 2 pi, but really pi modulo 2 pi. Why is that? So here is a local picture for the dual graph of G. You have a dual vertex here, and around it in cyclic order, turning in clockwise order, you will have dual vertex 1, 2, 3, and 4. An embedding means that the cyclic order of the dual vertices is preserved, while here you don't have an embedding because you have a different cyclic ordering of the vertices. So from now on, I'm going to only consider embeddings of the dual graph, and you see that when you have an embedding of the dual graph, the sum of every other angle is comprised strictly between 0 and 2 pi. So if it is 0 modulo pi, it has to be equal to pi modulo 2 pi. And saying that the sum of these two angles is equal to pi modulo 2 pi means the following. You can rewrite each of these angles as some argument. So for example, this is argument of z4 minus z0 over z1 minus z0, and saying that this sum is pi means that this ratio has to be a negative real number. So what is this ratio? It's a ratio involving complex vectors connecting z0 to its 4 neighbors. And this is an alternating product. I have this vector divided by that one times this one divided by that one. And what is important to note here is the orientation of these vectors. They are all pointing out of z0. And when I have something like that, I want it to be a negative real number. And this alternating product, which is real negative, this sounds very much like the Castellane sign condition, which we had in part 1. So we are very close here to the connection between circle centers and dimers, which I'm going to explain right now. So what is the connection? There's a correspondence between centers of circle patterns and dimer edge weights, and there are 2 directions. And the simplest direction, which I'm going to explain first, is how to go from circle centers to dimer edge weights. So let's fix some plain bipartite graph G, and we start with the setting of part 2. So this planar bipartite graph G will have a certain embedding. The dual graph will have some embedding as circle centers. And we are going to construct something like in part 1, where we had no particular embedding of the graph, but where we had some edge weights on each edge, which satisfied the Castellane sign condition. So how am I going to construct some edge weights on, so say I have an edge here between a black vertex B and a white vertex W. How to construct an edge weight on this edge? So I'm going to look, this edge separates 2 faces, and each face corresponds to a circle, which has a center. I'm going to connect the corresponding 2 centers and draw the corresponding vector in such a way that the black vertex lies to its left. So this vector is some complex number, which is determined by the way I drew my circle centers, and I'm going to assign that complex number to this edge. So to give you an example, if I start with this bipartite graph, then I'm going to orient the edges of the dual graph like this, and the edge weight I'm going to put on this edge, for example, is this complex number here, and so on. So why does this assignment of complex edge weight satisfy the Castellane sign condition? It's because of the following. If you have here a face of degree 4 in your bipartite graph, this means that your dual vertex has degree 4, and the orientation of the dual edges is the following, because of the colors of the vertices. So you will have an alternating orientation, 2 in and 2 out. And I told you at the end of the previous part that if you take the alternating product of all these vectors, but all of them pointing out of the central dual vertex, then this should be real negative. And now I'm just reversing the orientation of 2 of these vectors. So the condition is still that this alternating product should be negative. And in general, if you have a face of degree 0 modulo 4, it's going to be the same thing. Now if you have a face of degree 6, like here, you again have that the orientations alternate, and if you want to take the alternating product of all these complex edge weights, and you have them all pointing out of the center, then you know that it is negative. But with this orientation, you need to revert the orientation of 3 vectors. So the condition is that this alternating product of complex numbers should be positive. And in general, if you have a face of degree 2 modulo 4, then the alternating product should be positive. Another remark is that if you fix, for example, this white vertex and you look at the sum of the edge weights that I put on all the edges adjacent to that white vertex, then this corresponds to the sum of these 3 complex vectors. And because I have a closed face in my dual graph, these 3 complex vectors sum to 0. This means that around each vertex in my primal graph, the complex edge weights sum to 0. In other words, these edge weights have 0 divergence. So this is somehow, if you want to remember something from this talk, what you should remember. It's not really a theorem, but more of a guiding principle, which explains the correspondence between circle centers and diagonal edge weights. Whenever you have a bipartite graph, the geometric local condition that I described in part 2, being centers of a circle pattern with embedded dual, implies the local condition which I described in part 1, being Castellane edge weights with additionally 0 divergence. So this is something we discovered with Kenyon, Wayne Lamb, and Marianna and Russkikh last year. And the fact that circle center embeddings satisfy the Castellane condition was also observed independently and around the same time by Niklas Affolter. So in the first part, I told you that the classical way of thinking about the diamond model was to have positive edge weights. So if you have, I told you how to get complex edge weights. If you want to have positive edge weights, then instead of taking the vector connecting 2 adjacent centers, you should just take the distance between the corresponding 2 adjacent centers. And this would give you the positive edge weight to put on your diamond graph. So this was the simple direction, how to go from circle centers to diamond edge weights. And this is the simple direction because it is a local construction. If you want to construct a diamond edge weight, you only need to know the position of the 2 centers around that edge. And now we would like to go in the other direction. So somehow the question we want to ask is, we constructed some diamond edge weights from circle centers. How universal are these diamond edge weights? Can we recover any diamond edge weight like this? So let's start with a bipartite graph with positive edge weights or complex edge weights. Do these complex edge weights arise as some edge weights coming from circle centers? Clearly the answer is no, because if you take arbitrary complex edge weights around a given vertex, they are not going to sum to 0, while the edge weights I had coming from circle centers always sum to 0. So here you may be disappointed, but then you remember that what you care about is not actually the edge weights, but the gauge equivalence class. What you care about is the Boltzmann probability measure for the dimer model. So the question you should ask is, I start with a collection of edge weights on my graph. Can I find some gauge equivalent weights to these prescribed edge weights which do come from circle centers? And such a choice of gauge is called a Coulomb gauge, because it mirrors the fact that in physics, for the Coulomb gauge, you pick the divergence of the vector potential to be 0. So can we find a Coulomb gauge for arbitrary edge weights? And the answer is yes. But to answer this question, so you want to find some embedding of your geograph which will produce some gauge equivalent weights. I need to take a different definition of the geograph than the one you usually would take. So what is the geograph? Usually you put one geovertex inside each bounded face, and you also put one geovertex in the outer face, and you connect two geovertices whenever the corresponding faces are separated by an edge. And here you see in particular that you have 4 outer edges and 4 outer dual edges, and all the 4 outer dual edges go to the same outer geovertex. This is the classical notion of a geograph, but I'm going to consider a different notion of the geograph, where these 4 outer dual edges are going to be sent to 4 distinct outer dual vertices. So I have one outer dual vertex per side of my outer face, and I also decide to connect in a cycle these outer dual vertices, and I call this the augmented dual of my graph. And this is the notion of the geograph that I'm going to embed to get some dimer edge weights, which are gauge equivalent to my original dimer edge weights. So the setting is the following. You fix G to be a planar bipartite weighted graph, and for now let's assume that it has an outer face of degree 4. So question, can I find gauge equivalent weights coming from circle centers, from an embedding of this augmented dual as circle centers? The answer is yes, and the answer, how many of them are there, is actually infinitely many. So to go down to just a finite number of them, what I need to do is to prescribe certain boundary conditions. So what boundary conditions am I going to prescribe? I fix some convex quadrilateral P in the plane, and I require that my 4 outer dual vertices are sent to the vertices of that convex quadrilateral P. And then once I fix the position of these 4 outer dual vertices, there are only 2 embeddings of the circle of the 2 embeddings of the geograph, which will give you some circle centers which will produce gauge equivalent weights to your original dimer edge weights. So another way to say that is the following. Start with an unweighted bipartite planar graph with boundary length 4 and prescribe some boundary conditions, some convex quadrilateral. Then there is a 2-to-1 correspondence between, on the one side, embeddings of the augmented dual of G as circle centers, and on the other side, Boltzmann probability measures for the dimer model on G. So this is somehow the content of this dimer circle correspondence. It's a correspondence between some dimer probability measures and some embeddings of the geograph. So sometimes people think, well, the dimer model is a probabilistic model, so you should have some randomness on one side, and why is there no randomness on the side of circle patterns? It's because in your random model you have something which is deterministic. It's a probability measure, and the correspondence is between this deterministic object, the probability measure, and the embeddings. So far I've been assuming that my outer face has degree 4. It's actually a technical assumption, and we expect this to hold for more general boundary lengths, but maybe with more solutions. Here we have a 2-to-1 correspondence. As we increase the size of the boundary, we expect to have more solutions. Yes?
Is there an easy way to understand why it's 2-to-1 and not like 7-to-1?
Well, the way we prove this somehow is that we start with the simplest graph with boundary length 4, it's just a 4 cycle, and then we grow any graph, our favorite graph with boundary length 4, by performing some local moves for both dymographs and circle patterns. And when you solve for the base case, the 4 cycle, then you just have a quadratic equation, so you have 2 solutions somehow. And when you do the induction step, it doesn't change the boundary conditions and it doesn't change the number of solutions.
And that wouldn't change if instead of a square you had some kind of larger outer...
Right, so the induction step works for other boundary conditions, even if you have larger boundary conditions. But what we are missing for boundary length 6, 8, and so on is the base case, is to be able to solve the base. If we can just solve one base case for arbitrary, for each...
so that it could be that this base case give rise to a higher degree algebraic equation.
Exactly.
So you would have not 1 to degree.
Exactly.
Yeah, I see.
Okay, is there some symmetry between the 2 solutions, the 2 cases? Or is
there is some symmetry when you take the 4 cycle. Then it's some geometric symmetry, but it's a bit more complicated when you have a larger graph. Other questions? So this was the setting of a finite planar graph. You can also look at another interesting setting. For example, if you want to look at the infinite square grid with periodic weights. Or more generally, you can take the setting of infinite planar bipartite graph, which are periodic in 2 directions. And you also require that the edge weights are periodic. So here you see, for example, that you have some fundamental domain, which is repeated infinitely often. So when you have an infinite planar graph, you no longer have a Boltzmann measure, because you can't just have the weight of a dimer covering, because it involves a monomial with infinitely many terms. What replaces the Boltzmann probability measure is the notion of Gibbs measure. So what is a Gibbs measure? It's a probability measure on dimer coverings of your infinite graph, such that whenever you have a finite subgraph of that infinite graph, and you constrain the configuration outside of that finite subgraph, then the conditional measure induced on that finite subgraph is nothing but the Boltzmann measure induced by the edge weights on that finite subgraph. So it's a generalization of Boltzmann measures to infinite graphs. Gibbs measures for the dimer model are not unique in general. There is an entire convex set of Gibbs measures, and the extremal points of that convex set are called ergodic Gibbs measures. These are Gibbs measures which are not convex combinations of other Gibbs measures. And among all these ergodic Gibbs measures, I'm going to consider a specific subclass of them, which are called the liquid ergodic Gibbs measure. An ergodic Gibbs measure is called liquid if the correlations between edges decay polynomially with the distance between edges. So this may seem a little bit abstract for now, but there is somehow a concrete way we manage to have a grasp on the space of liquid ergodic Gibbs measures. It's by using the amoeba, which is associated to that infinite planar bipartite graph. I don't have the time to explain exactly what it is, how to construct it, but in a few words, whenever you have an infinite planar bipartite graph which is periodic in 2 directions, you can associate to it some algebraic curve called the spectral curve. And then you can represent that algebraic curve in log-log coordinates, and you get what is called the amoeba. So here's a picture, for example, of an amoeba with 4 infinite branches and a hole. And the interior point of this amoeba parameterize the liquid ergodic Gibbs measure. For each interior point of this amoeba, you have exactly 1 liquid ergodic Gibbs measure. This is a result of Kenyon, and Sheffield. So for this setting, infinite biperiodic graphs, we have the following result. So if you start with an infinite weighted bipartite graph periodic in 2 directions, then you want to construct periodic embeddings of circle centers of the dual graph of G, which produce edge weights which are gauge equivalent to your original edge weights. And here again, you have infinitely many possibilities. But actually, you can somehow count how many possibilities you have for each liquid ergodic Gibbs measure that you have for your dimer graph. You have exactly 1 circle center embedding, one periodic circle center embedding of the dual graph. So what I want to stress is that both in the case of finite graphs and in the case of infinite biperiodic graphs, the construction to go from circle centers to go from dimer edgeways to circle centers is complex. It's complicated because it's non-local. If you want to reconstruct your embedding locally, you need to have all the information for all the graph. You need to go all the way to the boundary of the graph. It's not a local construction. So this was the description of the dimer circle correspondence, and now why do we care about such a correspondence? So first, what can we do with such a correspondence? The first thing we did was to answer the conjectures that I exposed in the seminar last year, which involved some dynamical system which was defined entirely geometrically. There was no statistical mechanics, only some discrete dynamics in geometry. This dynamics is called Miquel dynamics because it is based on classical theorem of geometry called Miquel's theorem, which is the following. You start with four circles: north, west, south, and east. North and west intersect in 2 points, A and A prime, west and south in BB prime, south and east in CC prime, and east and north in D and D prime. Then Miquel's theorem tells you that 4 of these points, A, B, C, and D, are concyclic, meaning that there's a circle going through all 4 of them, if and only if the other 4 points are also concyclic. So we use this theorem to construct a dynamical system. Because if we start with a configuration where we have 5 circles, a central circle surrounded by 4 circles in this configuration, then we can erase the central circle and replace it by another central circle. So this is how Miquel dynamics works. You start with some circle pattern for the infinite square grid at time 0. Then you perform a Miquel move, as I explained on the previous slide. So, sorry, I should say that your square grid carries a checkerboard coloring. Every face is colored alternately in white and black. And so first you start with a square grid. At time 1, you're going to do a Miquel move on every white face, every white circle. And then at time 2, you do a Miquel move on every black circle. And then you continue at time 3, a Miquel move on every white circle, and so on. This discrete time dynamics was invented by Kenyon, and I studied its first properties, first alone and then with Alexei Glutyuk. So I'm going to show you some mathematical animation for Miquel dynamics. Here's a portion of the square grid, 6 by 6, and I have some periodic boundary conditions. So in dashed lines I have the circles, circumcircles of a white face, and in solid lines I have circumcircles of black faces. So first I'm going to do a Miquel move on all the white faces. So you're going to see all the white circles change at once, and the black circles will not change. Here. Now I do a Miquel move on all the black circles, like this, and then you see I alternate white, black, black. So the conjecture was that this is a discrete integrable system, and that it is governed by some cluster algebra mutations. And actually, using the dimer circle correspondence, we can give a positive answer to that. Why is that? So we translate this problem from circles to dimers, and we observe that for the dimer model, we also have a local move. And that local move is actually the same as the Miquel move once we use the correspondence. So what is this local move for dimers? Local moves you can think of, if you want, you can think of resistor networks where you have local move, you have series move, parallel moves, which reduce your network and don't change your equivalent resistance. You also have the star triangle move, which changes the topology of your network, and you also have different edge weights, but it doesn't change the equivalent resistance. Here is the same. Whenever you have a bipartite graph on which you want to study the dimer model, if you have some face of degree 4 somewhere, you can erase the corresponding 4 edges and replace it by the following drawing with that change of edge weights. So delta is AC plus BD, and you put these edge weights. Then when you do this local change, it will not change the dimer correlations in your model. In that sense, it's a local move. And what we proved with Kenyon, Wayne Lam, and Marianna Russkikh, and which was also observed by Niklas Affolter, is that under the dimer circle correspondence, the Miquel move corresponds to that dimer local move called the urban renewal. What does that mean? It means somehow that if you start with some dimer graph and you want to find the Coulomb gauge, you want to find some embedding of a dual graph which will give you a circle centers, which will give you these dimer edge weights. This is a difficult construction, as I said. It's a global construction. But now suppose you can do it once, and you do a local move on your dimer graph. You get a new dimer graph. You would think that you have to do this construction all over again. But no, you don't have to do it all over again. You can just take your first embedding and do a local move and get the new circle center embedding. So this is actually quite important in the dimer circle correspondence. And in terms of geometric dynamics, of Miquel dynamics, this identifies Miquel dynamics with some discrete time dynamics defined by Goncharov and Kenyon on the dimer model. And because Goncharov and Kenyon showed that their dynamics was an integrable system governed by cluster algebras, we automatically deduce that Miquel dynamics is integrable and governed by cluster algebras. So let me just tell you very briefly how to see the cluster algebras here. So somehow it consists in revisiting Miquel's theorem. So Miquel's theorem tells you that if you have 5 circles like this, you can draw a 6th circle. And now you can place the centers of these 5 circles. And you can ask, is the center of the 6th circle a deterministic function of the centers of the 5 circles? It's not obvious, because the 6th circle is a function of the 5 circles, meaning it's a function of the 5 centers and the 5 radii. So it might not be the case that the 6th center is a function of the 5 centers, of just the 5 centers. But actually, the surprising answer is that the 6th center is a function of these 5 centers. So if you give names to these 6 centers, C is the old center, C prime is the new center, and N, W, S, and E are the surrounding 4 centers, all of them seen as complex numbers. Then you have this relation between these 6 centers. So this is somehow revisiting Miquel's theorem 180 years after. We find still a new equation inside Miquel's theorem. And as you see, there is C prime appearing once in the numerator and once in the denominator. So you can solve this equation for C prime, and it has a unique solution, C prime as a function of the other 5 centers. This equation is called the discrete Schwarz-KP equation. So this governs Miquel dynamics, but it's also known to govern other interesting geometric dynamics, such as the pentagram map, the Laplace-Darboux transformations, and some dynamics using Clifford chains of circles. And so where are the cluster algebras? So I'm going to explain this for the dimer model, but it's the same for circle centers. You just need to translate from circle centers to dimers. In the dimer model, I told you that you have an X variable, capital X variable, attached to each face. Capital X variable, which was equal to the alternating product of the edge weights around the face. So if you have a central face here with X variable X0, and the surrounding 4 X variables are here, then after doing urban renewal, let me denote by X0 prime the new X variable, it's nothing but the inverse of the old X variable. And the new X variable in the northern face, X1 prime, is equal to the old X variable in the north face, X1, multiplied by 1X0, and so on. So these are actually the evolution for a Y system for coefficients in cluster algebra mutation. So this is the relation between Miquel move and cluster algebras. So this is one of the application of the dimer-circle correspondence, and it was an application to the geometric dynamics. Now you may want to also have some application to statistical mechanics. And more precisely, what we would like to have is, given a StatMech model, find some embedding adapted to the statistical mechanical model. So what is the question? You fix, say, an infinite planar graph periodic in two directions, and you want to study some statistical mechanical model on that graph. Dimer model, but also a random walk or Ising model. A major question is to find some universal embedding of that graph, such that in the limit, in the scaling limit, you will see some conformally invariant objects, such as Brownian motion or some SLE. The problem is that, as I said in part 1, these models, like the dimer model, are defined on graphs which do not carry any specific embedding. But when you want to see these conformally invariant objects, you need to prescribe first an embedding and then to take the scaling limit. So you need to find some, so when I say universal way to embed them is you fix a model and then you find an embedding which depends on the model, but some rule which somehow does not depend on the graph. It's sometimes very easy to do this when your graph is just the square grid and all your edge weights are 1, but it's a difficult question in general when you have an arbitrary graph, when your pattern, periodic pattern is arbitrary, and when your edge weights are arbitrary. So this is actually still an open field of research. And you have the same issue when you want to state the convergence of some random planar maps, maybe decorated by some statistical mechanical model. This will give you some random measure, for example, on the sphere, and you want to show the convergence of this random measure to Liouville quantum gravity. Here again, you need to specify some way of embedding your graph before you can formulate the convergence to Liouville quantum gravity. So actually this approach of using circle patterns to embed graphs to see Liouville quantum gravity in the scaling limit was pioneered here by François David and Bertrand Hénard and also Séverin Charbonnier. So our hope is that, what we expect is that these circle center embeddings are the adapted embedding to study the dimer model, both for regular lattices and for random lattices. And one reason why this is a reasonable hope is that for the dimer model you have this local move, urban renewal, and you also have a local move for the circle center embeddings given by the Miquel move. So this is one reason to believe that it's adapted. And there's a second reason to expect that this is the good embedding. It's because for two StatMech model, spanning trees and the Ising model, we know some adapted embedding. In the case of the spanning tree model, we know the Tutte embedding, and in the case of the Ising model, we know the s-embedding. And actually, these circle center embeddings for dimers, they generalize in some sense both the Tutte embedding and the s-embeddings in a way that I'm going to explain right now. So let me start with the spanning tree model. So you have some model, you have some planar weighted graph G, and on that graph G you study the spanning tree model, meaning that you look at the configurations are spanning trees of your graph. It's a subgraph which is connected and which reaches every vertex. And when you want to study the spanning tree model on an arbitrary graph G, there's a bijection called temporally bijection, saying that it's equivalent to study the dimer model on some graph G prime constructed from G. How do you construct that graph G prime? So say that here I have my graph G with vertices, with 3 vertices here. Then I can draw my dual graph, the graph which is dual to G, and I superimpose my primal and dual graph, and so I need to add also a vertex at each midpoint of each edge. So my graph G prime will have the vertices of my graph G prime. There will be one vertex for each vertex of G, one vertex for each dual vertex of G, so for each face of G, and one vertex for each edge of G. So then what I can do is to construct the Tutte embedding of that original graph G. What is the Tutte embedding? It's an embedding of both the primal and the dual graph of G in such a way that each pair of a primal edge and the associated dual edge is orthogonal. So it also gives you a position for the edge midpoint. You just put it at the intersection of the two lines. And the claim is that such a Tutte embedding gives you a circle pattern for G prime. Why? If you look at this face here of G prime embedded as a Tutte embedding, here you have a right angle, because I said that your two edges were orthogonal. And here also you have a right angle. So this means that this face is cyclic, that there's a circle around this face. And this Tutte embedding gives precisely the circle center embedding for that graph G prime. So in that sense, the circle center embeddings generalizes the Tutte embeddings, which is adapted to the spanning tree model. This Tutte embedding was used, for example, in very recent work by Gwynn, Miller, and Sheffield to prove the convergence of a model of maps decorated by trees to Liouville quantum gravity. The other thing that it generalizes is s-embeddings. So s-embeddings were introduced very recently by Dima Cherkak as some embeddings adapted to the Ising model. So the setting here is that you want to study the Ising model, which is a model of magnetization on some planar weighted graph G. Actually, if you study the double Ising model on that graph G, there's a correspondence by Wu Lin and Jubeda, which says that it's equivalent to study the dimer model on some planar bipartite weighted graph G tilde obtained from G in a certain way. And the way it is obtained means that the faces of that new graph G tilde will be of three types. There will be some faces of G tilde which corresponds to a vertex of G, some faces of G tilde correspond to a face of G, and some faces of G tilde correspond to an edge of G. On the other hand, Cherkak tells you how to embed each vertex of G, each face of G, and each edge of G as an s-embedding. So what's an s-embedding? It's a way to draw each primal vertex, so each edge of your primal graph, and each dual edge, each dual vertex, in such a way that when you look at a quadrilateral connecting these two primal edges and two dual edges, then this quadrilateral should be a tangential quad, meaning that there exists a circle which is inscribed inside that quad. And the way that he places the point associated to the edge is by placing it at the center of that inscribed circle. So in general, this center is neither on the primal edge nor on the dual edge. So maybe this picture is a little bit misleading. And then you can do the same here. You have a way to place each vertex of G, each face of G, and each edge of G. So it means that you have a way to place each dual vertex of G tilde. And actually, this gives you precisely the circle centers for G tilde. So again, these circle centers generalize the s-embeddings. And my last slide. Yes?
Just one question. This s-embedding is motivated by holomorphicity, by discrete holomorphicity?
Yes. Yes. So so this is what we can somehow prove, and now what would we like to prove additionally using these circle center embeddings? One thing we would like to prove are local formulas for the correlations and for the free energy, for the dimer model. So what is that? When you have a dimer graph and you want to compute the correlation between two edges, this depends globally on the graph, meaning that if I change the edge weight of an edge far away from these two edges, it will change the correlation between these two edges. But it's somehow the same for the circle centers embedding. If I want to compute the circle center embedding of a graph, I want to compute it locally, then if I change some dimer edge weight very far away, it will also change my circle center embedding at the place I'm interested in. And one might hope maybe that, okay, you start with a dimograph, you have some complicated process which gives you the construction of the circle centers, but maybe once you have the circle centers, then everything becomes local, meaning that if you know the embedding of your graph in a small region, then you can compute the dimer correlations only from knowing the local geometry. So this might sound very naive or excessively optimistic, but actually there are already many results in this direction for certain specific subclasses of weights. For example, Kenyon obtained first results in this direction for isoradial graphs, which correspond to circle patterns where all the circles have the same radius. And there are also results for the spanning tree model, for the Ising model, for isoradial graphs, and a slightly more general class of graphs obtained by Kenyon, Cédric Boutier, Béatrice Detillière, and Kylian Rachel. So it's not unreasonable to think that you would have the same thing in the general case, and one reason to think that you have that is because of that local move. You can change things locally in both the dimer model and the circle patterns in a similar way. And the second type of results we would like to prove are results that Philippe Di Francesco is very familiar with, limit shape results. So let me explain this on just an example, the example of the Aztec diamond. So the Aztec diamond, this is the Aztec diamond of size 3, is a way to draw somehow a diamond on the square grid. You are carving a diamond on the square grid, and because here you have 3 corners, this is the Aztec diamond of size 3. You can consider the Aztec diamond of size n, for n very large, say n equals 200, and you pick one dimer covering of this graph uniformly at random. Then you see a picture like this. Here's the color code. You have 2 types of horizontal edges. Either the black vertex is on the left, and then you color it in red, or the black vertex is on the right, and then you color it in green. And similarly, you have 2 types of vertical edges, so 2 colors. Then what you see is a picture like this. And on this picture, you see some large-scale order. There is some sort of inscribed circle inside my diamond, and outside that circle, you see that in the northern region, you only see red dimers. And similarly in the other west, south, and east regions. And in the center, things are mixed, but you see there's still a bit more red when you go north. So this is the kind of limiting results that we would like to prove. There are already many results which are proven in this direction, but we are hoping that circle patterns would give maybe a unified approach to all these limit shape results. And to finish, I'd just like to mention that there is a paper by Dima Chelkak, Benoît Lallier, and Marianna Russkikh, which should appear very soon, in which they define some notion of discrete holomorphic functions on embeddings of geograph as circle centers, and they also study conditions under which these discrete holomorphic functions converge to actual continuous holomorphic functions. And that's all. Thanks for your attention.
Showed us a reformulation of Miquel's theorem as the product of cross ratios equal to -1, right? And I was wondering if this has anything to do with Plucker relations, you know, between Plucker coordinates. I think there is some relation like that the product of Plucker coordinates is equal to -1. Do you have any idea about that?
Not that I know of. Yeah, maybe you can discuss, but I don't know that.
So I have another question, which is related also to this connection to urban renewal and cluster algebra. So in cluster algebra, there's a natural way of quantizing things, which is in which cluster variables or whatever variables appearing in the model, like
Q commute instead of
become quantum. That is, there are operators and they have commutation relations and stuff like that. So is there a quantum version of Miquel's dynamics?
I don't know either. I don't even know what class of objects you should consider to.
Well, it's really like statistical models in which the Boltzmann weights become operators rather than just numbers. So, and I was thinking along those lines when I asked you a question of, is the complex number, can it be replaced by a matrix or by something that doesn't commute?
I see.
Right.
Well, I think there is a notion of quantum integrable system for dimers in the Goncharoff-Kenyon paper, but I must say it's something I don't yet understand quite well.
So their notion of integrability was with respect to the Poisson bracket with which you would quantize.
Yes.
Right. So they had a Poisson structure.
Yes.
And integrability was with respect to that.
What do you really mean by discrete holomorphicity that converge to holomorphic?
Well, there is some constraint that these functions need to satisfy locally, and then if some things are bounded, then if you refine the mesh, this will converge to some continuous holomorphic function, some actual holomorphic function.
This was already observed, I guess, in many models.
Yes, but here they have a very specific definition of discrete holomorphic functions. It's really some definition adapted to the case of circle centers. It's not the classical notion, I mean, one of the classical notions of a discrete holomorphic function. It's a new.
I had another question regarding the divergence-free condition that you showed us. Usually, well, at least in the type of statistical models we've been looking at, say with Emmanuel Guiter, there's always this question whether you can define a dual height variable. And usually the compatibility condition for a dual height variable to exist is that a condition like this is satisfied. So is there any hidden variable that you haven't shown us in those problems? Like you see, a variable which between two circle centers would differ by the vector. And therefore, this variable is well defined because when you go around, you end up with the same variable that you started from, right? Because the sum is 0.
Yes. So I think Machelkak has something like that when he studies the s-embeddings of the Ising model. There is some function like that he considers, but we didn't really consider that function. But you can, of course, define it.
See, because the interest about this variable is that if you can think of it as living in a higher dimensional space, then it can describe some different universality classes with different central charges of the underlying conformal field theory and stuff like this. It's like really a dimension of an embedding.
I see.
Okay. Thank you very much.